1958, Wright-Patterson Air Force Base, Ohio. 2 aircraft sit on the runway in the early morning frost. Both are experimental turboprops powered by identical jet core engines. Both built to test a question the Pentagon thought it already answered. The first uses a fixed-pitch propeller, modern, simple, sleek. The second, a constant-speed propeller design based on a system written off decades earlier as obsolete. Test pilot Lieutenant Colonel James Connors throttles up the first aircraft. Takeoff run, 400 yards, climb to 20,000 feet, 9 minutes 15 seconds, maximum cruise speed at altitude, 285 miles per hour. 30 minutes later, Connors climbs into the second aircraft. Identical airframe, identical engine, different propeller. Takeoff run, 280 yards, climb to 20,000 feet, 6 minutes 10 seconds. Maximum cruise speed, 385 miles per hour. Same plane, same engine, same Cold War hanging in the balance. The difference between air superiority and obsolescence came down to 3 spinning aluminum blades that jet-age engineers across America had dismissed as relics of a war they'd already won. But the story of how one stubborn engineer's equations defied an entire era's assumptions begins 8 years earlier, in a factory where everyone said the future belonged to jets alone. East Hartford, Connecticut, winter 1950. Robert McKenzie stood in the wind tunnel facility of Hamilton Standard Propeller Corporation on a grey February morning. At 42, the MIT-trained aeronautical engineer had the methodical bearing of a man who trusted physics over fashion. Wire-rimmed glasses perched precisely on his nose, slide rule never far from his calloused hands. Behind him, mounted on a test stand that vibrated with mechanical fury, spun a gleaming metal propeller unlike anything in modern aviation. 3 aluminum blades that could change their angle while rotating at 2,800 revolutions per minute, adapted for the new turbine engines that were supposed to make propellers extinct. The telephone call that would change everything had come 3 days earlier from Strategic Air Command headquarters in Omaha. The problem was simple, brutal, and classified. America's new B-36 Peacemaker, the intercontinental bomber designed to carry atomic weapons deep into Soviet territory, was failing its endurance tests. The massive aircraft could reach Moscow, but the jet engines burned fuel so rapidly that return missions were marginal at best. Entire bomber wings sat grounded, while Washington debated whether nuclear deterrence was even achievable with current technology. General Curtis LeMay had delivered an ultimatum that morning. Extend the range or we're redesigning the entire strategic doctrine. The stakes couldn't be higher. The Soviet Union had detonated its first atomic bomb in 1949, shattering America's nuclear monopoly. The Cold War had frozen into a technological arms race, where air superiority meant survival and obsolescence meant annihilation. Mackenzie had heard this song before. Across America's aviation community, the conventional wisdom flowed like gospel from hangar to boardroom. The jet age had arrived and propellers belonged to history. Too slow for the supersonic future, too primitive for the missile era, too simple for the complex demands of nuclear warfare. The Air Force Strategic Command had officially classified turboprop engines as transitional technology at best. Even Lockheed's chief engineer had publicly stated that any aircraft still using propellers in 1960 will be a museum piece. But Mackenzie possessed the quiet confidence of an engineer who had learned from the man who had been proven right before. His father had worked under Frank Caldwell at Hamilton Standard during the war, had watched aviation experts resist constant-speed propellers because fixed pitch was simpler. Each time, Caldwell's data had demolished their assumptions. Each time, the industry had eventually followed where the numbers led. This time felt different. This time, the entire philosophy of American air power was at stake. Hamilton Standard had invested everything in Mackenzie's turboprop adaptation. 1,200 jobs in East Hartford, plus manufacturing contracts that stretched from Connecticut to California. The company that had equipped every Allied fighter in World War II might not survive if Mackenzie's calculations proved wrong in the jet age. His own reputation, built over 18 years of propeller development, rested on a simple proposition that contradicted everything the Air Force believed: that an obsolete World War II technology, properly adapted, could outperform the jets everyone worshipped. The engineering was elegant in its persistence. Caldwell's original system had used engine oil pressure to automatically adjust blade angle based on flight conditions. McKenzie's adaptation did the same, but for the new Allison T-56 turboprop engine, a hybrid power plant that combined jet turbine efficiency with propeller thrust. During takeoff and climb, the propeller automatically shifted to fine pitch, like a car's low gear, allowing the engine to develop maximum power. At cruising altitude, the system shifted to coarse pitch for maximum speed and fuel efficiency. The blades constantly adjusted, finding the perfect angle for every flight condition without pilot intervention. The numbers spoke with mathematical certainty. McKenzie's wind tunnel tests at MIT had proven that constant speed turboprops could increase endurance by 60%, extend operational range by 800 miles, and improve fuel efficiency by 25% compared to pure jets. But numbers meant nothing if the Air Force refused to believe them. The breakthrough came on March 3, 1951, when Strategic Air Command gave Hamilton Standard one final chance. One test flight with their impossible propeller installed on a modified C-97 cargo aircraft. Test pilot Major Eddie Rickenbacker Jr., son of the famous World War I ace, would put McKenzie's theory to the ultimate test over the same long-range profile that had grounded pure jet designs. Edwards Air Force Base, California, March 3, 1951, 0600 hours. Rickenbacker climbed into the cockpit of aircraft serial number 49-2592. 4 Allison T-56 turboprop engines, each equipped with McKenzie's constant speed propeller system. The mission profile was brutally simple. Simulate a round-trip strategic bombing mission to maximum range, then return with fuel reserves sufficient for combat maneuvering. The pure jet aircraft that had attempted this profile 3 weeks earlier had failed catastrophically. Maximum range, 2,100 miles one way. Return impossible without mid-air refueling that didn't yet exist operationally. Rickenbacker advanced the throttles. The constant speed propellers adjusted automatically, finding optimal pitch for maximum takeoff thrust, while maintaining engine RPM in the safe operating range. Where the jet aircraft had required 5,200 feet of runway, the turboprop lifted off in 3,800 feet. The climb was equally dramatic. At 10,000 feet, 15,000, 20,000, the propellers continuously adjusted to decreasing air density, maintaining engine efficiency while maximizing thrust. At 25,000 feet, where the jet aircraft had gasped for thin air and fuel, the turboprop cruised with authority. The numbers came back via radio telemetry, each transmission confirming what McKenzie's equations had predicted. Cruise speed at 25,000 feet, 320 miles per hour, only 40 units slower than the pure jet. Fuel consumption, 42% lower than jet engines at equivalent power settings. Maximum range at current fuel load, 3,400 miles. Combat radius with reserves, 300 miles. Rickenbacker flew the complete profile. 6 hours outbound, simulated bomb run, 6 hours return. When he touched down at Edwards, the fuel gauges showed 18% remaining, enough for another 200 miles or 45 minutes of combat maneuvering. Strategic Air Command received the test results by classified courier that evening. Turboprop propulsion exceeds all range and endurance requirements for strategic bombing missions. Recommend immediate evaluation for operational deployment. But as orders trickled into Hamilton Standard's East Hartford facility, a darker reality was emerging on the global stage. Tupolev Design Bureau, Moscow, November 1952. 1,500 miles east, Soviet engineers faced the identical problem from the opposite direction. Andrei Tupolev, Stalin's chief aircraft designer, stood before a wall-size schematic of the Tu-95 bomber. The aircraft was designed to carry thermonuclear weapons across continents, to reach American cities from Soviet airfields, to prove that the correlation of forces had shifted eastward. But the Tu-95 had the same fatal flaw as America's B-31. Pure jet engines couldn't provide the range Soviet strategic doctrine demanded. Tupolev's solution was heretical by Soviet standards. Turboprop engines with contra-rotating propellers, each blade angle controlled by a hydraulic governor system that adjusted automatically to flight conditions. The engineering team had discovered the same physics McKenzie had proven in Connecticut. They called it automatic pitch regulation. The Americans called it constant speed propeller control. Both sides had independently resurrected Frank Caldwell's obsolete World War II innovation, each believing it their own secret advantage. The irony would have amused Caldwell, had he lived to see it. Physics, unlike ideology, recognized no borders. East Hartford, Connecticut, June 1955. McKenzie sat in a classified briefing at Hamilton Standard's secure facility. The photographs spread across the conference table showed something that made his blood run cold. Satellite reconnaissance of a massive Soviet bomber, 4 engines, each turning enormous contra-rotating propellers. The CIA analyst's voice was clinical. We're calling it the Bear. NATO designation, 295. Intelligence indicates operational range exceeding 8,000 miles unrefueled. Maximum speed, 575 miles per hour. Service ceiling, 45,000 feet. The numbers hit McKenzie like a physical blow. The Soviets had taken the same principle Hamilton Standard was perfecting, constant speed propeller control, and built it into the backbone of their strategic bomber force. The machine designed to carry thermonuclear weapons to American cities ran on the same obsolete technology that Air Force planners had mocked 5 years earlier. A colonel from Strategic Air Command leaned forward. How is this possible? Our intelligence said Soviet aviation was a decade behind American technology. McKenzie studied the photographs. The propeller blade angles, the governor housings, the hydraulic lines. Everything screamed the same engineering solution he'd been developing since 1950. It's possible, McKenzie said quietly, because physics doesn't care about politics. We both discovered that jets can't win a range war. The Soviets just believed their own engineers faster than we believed ours. The room fell silent. The Cold War's defining irony was taking shape. Both superpowers had independently rediscovered and perfected the same impossible technology that conventional wisdom said belonged to the past. And now both sides' nuclear deterrence depended on propellers that were supposed to be extinct. Strategic Air Command Headquarters, Omaha, Nebraska. September 1956. General Thomas Power, LeMay's successor as SAC commander, stood before a wall-sized map of the Soviet Union. Red circles marked known bomber bases. Blue lines showed B-52 bomber routes, the new jet bomber that was supposed to render turboprops obsolete. The briefing officer's report was devastating. Sir, current B-52 combat radius without refueling, twin 900 miles. Soviet 295 combat radius, 4,800 miles. The enemy can reach our cities from bases we can't strike. We need tanker support for missions they can fly unrefueled. Power turned to McKenzie, who'd been brought in as a civilian consultant. You're telling me we bet our entire strategic bomber force on jets, and the Soviets bet on your propellers? Not my propellers, sir. Caldwell's propellers. We just adapted them for turbine engines. So did they. And they work? McKenzie pulled out performance charts. The Tu-95 proves the concept, but we have options. The Lockheed L-188 Electra, the C-130 Hercules, the P-3 Orion. Everyone uses turboprop engines with constant speed propellers. We're already building the technology into our transport, reconnaissance, and anti-submarine aircraft. We just need to admit it works better than pure jets for endurance missions. Power studied the charts. The mathematics were undeniable. For strategic reconnaissance, maritime patrol, airborne early warning, electronic warfare, any mission requiring aircraft to stay airborne for 8, 12, 16 hours, turboprops dominated jets on every metric except raw speed. How long, Power asked, until we can field aircraft that match Soviet endurance? Sir, we already have. The E-2 Hawkeye just completed carrier trials. Endurance, 6 hours on station. The P-3 Orion enters service next year. Range, 5,400 miles. The C-130 is operational now. We didn't lose the technology race. We just convinced ourselves we had. North Atlantic, April 1962. A US Navy P-3 Orion patrol aircraft cruised at 25,000 feet, 400 miles east of Newfoundland. 4 Allison T-50 turboprop engines, each turning a 4-blade constant-speed propeller, had kept the aircraft airborne for 11 hours. The mission: track Soviet submarines attempting to reach American coastal waters undetected. In the cockpit, Lieutenant Commander David Chen monitored fuel gauges that still showed 4 hours of endurance remaining. The same mission in a pure jet aircraft would have required 2 mid-air refuelings and 3 different aircraft to maintain continuous coverage. Below, in the Black Atlantic, a Soviet submarine maneuvered desperately, trying to shake the persistent American aircraft that had been tracking it since dawn. The submarine captain had never imagined American patrol aircraft could remain on station this long. Soviet naval doctrine assumed jet aircraft would exhaust their fuel and depart within 3 hours, providing a window for submarine movement. But the P-3's constant speed propellers had changed that equation entirely. Chen keyed his radio. Home plate, this is Sierra 2-3. Contact maintained for 11 hours. Fuel state sufficient for another 4 hours on station. Designating target for surface units. The submarine surfaced 6 hours later, forced up by American destroyers that had been vectored into position by an aircraft that simply wouldn't leave. Back at Patuxent River Naval Air Station, McKenzie reviewed the mission report. 11 hours airborne, 2,400 miles covered, continuous tracking of a submarine that thought it was safe. The constant speed propeller, the obsolete World War II technology, had just proven itself the silent guardian of American maritime security. Vietnam airspace. December 1967. A C-130 Hercules cargo aircraft held station at 15,000 feet over the A Shau Valley. 4 T-56 turboprops had kept the aircraft airborne for 9 hours, providing continuous logistics support for special operations teams operating deep in enemy territory. The aircraft commander, Major Frank Romano, watched fuel gauges that showed 3 hours of endurance remaining. Below, American soldiers depended on the supplies, ammunition, and medical evacuation capability that Romano's aircraft provided. Pure jets couldn't do this mission. They burned fuel too fast, required too much runway, couldn't loiter at low speeds over rough terrain. But the C-130, with its constant speed propellers automatically adjusting to flight conditions, could orbit for hours, land on jungle airstrips, and return for another mission the same day. Romano had flown 247 combat missions in Vietnam. Everyone depended on technology the Air Force had once dismissed as obsolete. Command, Hercules 2-1, resupply complete, returning to base. Fuel state sufficient for alternate airfield if primary is under attack. The voice that came back was grateful. Roger, Herc. You just saved 12 lives down here. Again. Romano smiled. The propellers that were supposed to belong in museums were saving American lives every single day. Arctic Circle, March 1970. A Soviet Tu-95 Bear bomber cruised at 40,000 feet, 200 miles north of Alaska. 4 Kuznetsov NK-12 turboprop engines, each turning massive contra-rotating propellers, had kept the aircraft airborne for 14 hours on a strategic reconnaissance mission probing American air defenses. Below, American F-4 Phantom jets scrambled to intercept, their afterburners screaming, fuel gauges dropping precipitously. The Soviet aircraft commander, Colonel Viktor Petrov, maintained cruise speed, slow by jet standards, but sustainable for hours longer than the American interceptors could remain airborne. The F-4s approached, photographed the Soviet bomber, then peeled away after 20 minutes on station. They had to return to base before fuel exhaustion forced them down. Petrov continued his mission for another 6 hours. The constant speed propellers that Soviet engineers had perfected kept turning, kept adjusting, kept providing the endurance that jet aircraft simply couldn't match. Both sides now understood the truth. Speed won headlines, but endurance won the actual Cold War. East Hartford, Connecticut. November 1989. Robert McKenzie, now 81, sat in his garage workshop, polishing an old Hamilton Standard propeller hub, a relic of 2 wars and 4 decades of technological revolution. On the television mounted to the wall, news anchors reported scenes from Berlin. The wall was falling, the Cold War was ending. McKenzie watched young Germans dancing on concrete that had divided a city for 28 years. He thought about the aircraft that had kept watch during all those years, American P-3s and E-2s and C-130s, Soviet Tu-95s and Tu-142s, all of them turning constant speed propellers that were supposed to be obsolete before the wall went up. The phone rang. It was his son calling from Hamilton Standard's engineering division. "Dad, you watching the news?" "I am." "Thought you'd want to know. We just got a contract extension. Navy wants another 200 P-3 upgrades. Air Force is extending C-130 service life to 2040. Those propellers you fought for 40 years ago? They're outlasting the entire Cold War." McKenzie looked at the propeller hub in his hands. Frank Caldwell had designed the original system in 1932. McKenzie had adapted it for turboprops in 1950. Soviet engineers had independently perfected the same principle. Now, in 1989, with one empire collapsing and another claiming victory, the machines kept flying. They'll probably outlast us all, McKenzie said. In 2025, 75 years after Mackenzie's first turboprop tests, both aircraft families still patrol the skies. American C-130 Hercules transport aircraft, designed in 1954, remain in frontline service with more than 40 air forces worldwide. The constant-speed propellers that were supposed to be obsolete have logged over 1.5 million flight hours. Soviet Tu-95 Bear bombers, first flown in 1952, still conduct strategic patrols from Russian airfields. The contra-rotating propellers still turn at the same RPM Tupolev's engineer specified 7 decades ago. The E-2 Hawkeye, the P-3 Orion, dozens of variants and derivatives, all flying on the same impossible principle that Frank Caldwell proved in 1933 and Robert McKenzie defended in 1951. History remembers the loudest inventions, the missiles, the jets, the satellites. But sometimes it's the quiet ones, the ones that never stop turning, never stop adjusting, never stop finding equilibrium through resistance, that actually shape how the world survives. The Cold War ended not because one side built faster machines, but because both sides built machines that could outlast the ideology that created them. And deep in the Arctic, over distant oceans, above battlefields that changed and borders that shifted, the constant speed propellers kept turning. Fine pitch for takeoff, coarse pitch for cruise, automatic adjustment for every altitude, every temperature, every flight condition, finding the perfect angle through mathematics, not doctrine, surviving through physics, not politics. Still turning long after the empires that built them stopped believing in absolutes,